Section 4.2, we're going to compute the least square regression line. We're going to use that line to make predictions, interpret the slope and y-intercept, and then compute the sums of the squared residuals. Okay, so we have our table here. We have our x values and y values. In Algebra 1, Algebra 2, we've dealt with slope, equations of lines, and this is no different, but we're going to have large sets of data, and we're going to compute the line ourselves. Rather than just getting 2 points, we're going to have a multiple array of points. So here we have x and y. Now, using your slope formula of your y's over your y2's minus y1 and x2 minus x1, from this set of data, we took the point 2 and 5, 7, 2, 5, 7, and 6 and 1.9. We took those 2 points, took the slope, found the y-intercept, and we came up in a line using all these points. But that's just using 2 of these points. So if we graph this line, the scatter plot, and we graph the line that we computed, and we're going to predict x equal 3, and you can just see that it's 4.75. But if you go back to the list, we have 5.2. That difference is called the residual, where we take the observed y, the one that was given to us in our data point, which is that right there, 5.2, and the one we predicted from our least squares regression line, and that's what we call a residual. The least square regression line is the line that minimizes the sum of all the errors, what we call residuals. It's the line that minimizes the sum of the squared vertical distance between the observed values of y and those predicted by the line, red y hat. Now that seems like a lot in that definition, but it really does. It just takes the difference of all the errors and minimizes that to make the best line possible using all the points, not just 2 random points within the data set. Now, once again, we're going to use the calculator to do a lot of the work for us, but it is something to make note of what really is happening. Okay, we have y hat, we have b1, where if you could see, really, it's the r, which we've already computed, and the sample standard deviations of both the y and the x. So you can see how it becomes a little bit complicated, but with the use of the calculator, we can go back and do it. So I'm going to pull up the data set from that we used in 4.1. Okay? And we're going to find the least square regression line, predict the drilling time if drilling starts at 130 feet. Is the observed drilling time at 130 feet above or below average? That would be our residual. So we're going to predict at 130, and we already see that on the table at 6.93. And then we're going to draw the least square regression line. So let's see how this comes out. Once again, let's go back to our line. If I go back to stat, edit, it's already in there in L1 and L2. So I can go back to stat, scroll down to 4, and there's my line. So the first part, A, is this line right here. And you can see, notice, it's 0.115 rounded off to 4 decimal places, 1110116. And our y-intercept in this case would be 5.5273. B, predicted drilling time for starts at 130. Well, I just plug in 130 into that, and there's other ways to do that other than just plugging 130. You can put this into a line, look at your table of values, and either way you get 7.035. And we're going to compare that to the observed as we looked at was 6.93, and that makes the residual below average. Here is our scatter diagram. along with the least squares regression line. Now notice I didn't actually plot the y-intercept, but I plotted usually the point from the first scatter to the last and see where the line fits. Now we have to interpret the slope. The slope of the regression line is 0.0116. That's basically right here. Okay? Really, we're going to interpret it. So really it's over 1. So it's like saying for each additional foot of depth, the time to drill 5 feet increases by that particular amount of time. The y-intercept is not always appropriate. Sometimes it is and sometimes it's not, depending on what it represents. In this case, to interpret the y-intercept, is 0 a reasonable value for the explanatory variable? Do any observations near x equals 0 exist in the data set themselves? Well, our y-intercept is 5.525. Let's go back to our data table, and 5.525 is it near our data set? And it is. I mean, you can see all the values are very close to 5 to 7. So yes, it is reasonable for this drilling data to be 5.5273. There are plenty of times where it won't be. Talking about, if you're talking about age and you get a negative y-intercept, well, clearly you can't be a negative number, so something like that wouldn't make sense. So you're talking about baby's weight. Well, if it's 0 or there is no y-intercept, that's also impossible too. Read at your discretion. Once again, we're going to compute the sum of the squared residuals. Well, the sum of the squared residuals is just the r squared. Here's r, the linear correlation coefficient when we're looking at the linear regression, and the least squares sum squared.